Okay, so this is your typical ignition coil, single post in your average non-coil on plug vehicle. These are high energy ignition ones that primarily General Motors, but you found these on Ford, you found them on Chrysler's. Other coil designs, such as those used on GM's high energy ignition, use an air-cooled epoxy sealed E-coil. Right now, notice the shape. You look at it and you could see an E in the actual framework of that coil. The E coil is so named because of the laminated soft iron core is E-shaped with the coil wire turns wrapped around the center finger of that E and the primary winding wrapped around the secondary winding. So we have one of these in the classroom, and it's a shame not to be able to show it to you now, but this here, notice the thickness of that wrapping. That's your primary winding that's wrapped around. And notice this giant area over here, right? This is your secondary winding. So you got this little one for your primary and this big one here for your secondary. So you can envision how we magnetize this, this overruns this, and then we get movement in that one. There's your E. This picture over here is a typical air-cooled epoxy filled one, and you can find this on many, many different cars, right? So this is showing a cutaway over here. So this is how your average side goes. Now remember what I said earlier. We generally run power to a coil and we control the ground side. But we could find a car that we run ground to the coil and control the positive side. When you think about it, it doesn't make a difference which way we do it. The current's the same on both ends. Whatever happens on one side can be controlled on the other. So we can control it either way, all depending on how the vehicle, the engineers decide to do it. All right, so traditional. The ignition switch power flows to the positive side of the coil. Power flows through the negative side of the coil via the primary winding coil. Ground is supplied by the igniter, the ignition control module, or the PCM to close that primary circuit. The current of 2 to 6 amps, and I want you to pay attention to this, right? This is what we have to work for. The current of 2 to 6 amps flows through the primary windings, creating a magnetic field. The magnetic field builds in the primary windings, and when we get to that maximum magnetic field strength, it's called saturation. When the ground path to the negative side of the coil opens, the magnetic field collapses, causing 12 volts to become 250 to 400 volts, which induces 20,000 to 40,000 to 80,000 to 100,000 or more voltage with the current flow of 0.02 to 0.08 amps in the secondary windings via induction. It took us 2 to 6 to make 0.02 to 0.08 amps in that secondary. This is why you don't die when you get shocked by spark. This is, however, why with distributorless ignition making 120,000 volts, you can cause the heart to skip a beat. You can hurt someone who has a heart condition by it because the amperage is a little bit higher than they are for your traditional system. High voltage exits the coil tower and jumps across the air gap at the electrode of the spark plug. The spark duration ignites the air-fuel mixture in the combustion chamber, and this happens repeatedly at every cylinder that reaches the power stroke. So what you just saw there has to happen on every let's say, put it this way, for every cylinder, every RPM that engine's running, right? So think about when you were doing 5 or 6 or 7,000 RPM, that has to go through that cycle of supply, magnetic field, collapse, poof. Supply, magnetic field, collapse, poof. Right? Over and over and over again. Think of how fast that has to happen. This is a typical system. And if you look at this, this has a distributor in it. Notice over here, we have a ballast resistor. In the olden days, notice this is the ignition switch right here. Here's the starter solenoid. This is our coil. That's the 2 sets of windings. There's your primary, there's your secondary. Notice here, the primary windings, 200 turns. The secondary windings, 20,000 turns. Notice over here we have a power transistor, right, an electronic module. And here we have a distributor. That's a distributor cap. It's showing the rotation. And here's our spark plugs at the end of our spark plug wires. You can see here that this makes 25,000 volts at 20 to 80 milliamps, right? So that's 0.02. Now, this ballast resistor, old cars had it because we didn't put a full 12 volts to a coil. We put 7 volts or 9 volts, and this was to drop it down. Now, naturally, it's a resistor. So what do you think happens to a resistor when we resist current? It gets hot. So this is generally a protected wire with a ceramic base for this ballast resistor that would run from the ignition switch under the dash out to the engine compartment. And back then they would burn up. So if you end up buying an old car, you might find a system that has this on there. But you'll see here, this is the pickup coil. This lives inside the distributor. So what happens? We have power going to this side. It comes all the way out the other side until the transistor toggles to ground. When it toggles to ground, it energizes this one, this bigger one here. This gets magnetized and induces this one. This rotates. Now, pickup coils, most of them have a magnetic type of signal too. And I love being able to show this to you in the classroom. I hook up a distributor to a drill and we look at the AC voltage we can make. But these points are magnets. Now this rotor, the shaft turns, and when this touches this, we have a magnetic field. As soon as it passes it, the magnetic field breaks, we get an AC voltage goes back to our module and tells when to click this. Once this goes through its cycle and the spark comes out of it, it races down here into the coil tower, and then there's a rotor inside, a distributor rotor, that now sends that center spark out the particular spark plug that goes out to our spark plug wires.